Hello everyone, Professor Gurbanov is here, and today I will try to explain the term of concavity when our function is going to be concave up and when our function is going to be concave down. So before starting our explanation, I would like to graph the graph of y equals x cubed. So if we sketch the graph of this function, let's say this is the point of origin, you can see that our function is not straight, it's not linear, and we have two type of arch kind of looking shapes. These shapes are called concavity, and you can notice on the right hand side from 0 to positive infinity, our graph is pointing upwards, our arch is pointing upwards. So basically this means that in this part our graph is actually concave up, because it makes sense, it's pointing upwards. Like that doesn't take a lot of knowledge to understand. And then here it's the opposite, so it's pointing downwards, so it is what? Concave down. So as you can see, visually, we have seen what concave up and what concave down means. Now let's try to connect it with our second derivative. Basically, our function is going to be concave up when for any continuous fx in a given range let's say I, if our first derivative of given fx is increasing in a given range I, then our function is going to be concave up. Now, if you have remembered, our fx, our f dash x is going to be increasing when its derivative is greater than 0. So in this case, our second derivative of a given function fx should be greater than 0 in the range of I, and that for it to be concave up. And for it to be concave down, it should be negative, because negative people always go down. So for fx, so at this point, our first derivative of fx should be decreasing in the range of, let's say, I, and our second derivative of fx should be less than 0. So this is the connection between concavity and the second derivative. Now, I would like to briefly touch the point of inflection, because in the point of inflection, our concavity changes sign, or visually I'll say, if you notice, at some point our graph is pointing towards downwards, and then it's pointing towards upwards. So at this point, if you can see it, it's changing direction, because for the left of this point, it's going concave down, and the right side is going concave up. So our point of inflection is a point for which, if logically saying, in this in our second derivative of, let's say this, we call this function y. So second derivative of y is going to be greater than 0, second derivative of y is going to be less than 0. So if you use a bit of logic, you might have understood that at this point, our function actually changes sign at some point in this interval. And when our second derivative of a given function changes sign, that point is called the point of inflection. And in this case, let's first of all find our second derivative of y. The first derivative of y is going to be 3x squared, and the second derivative is going to be 6x. So in this case, when our second derivative is 6x, for x in range 0 to positive infinity, our second derivative of y is going to be greater than 0. As you can see, our function is concave up. And for, let me write it from here, and for second derivative of y, when it's less than 0, so from correction, it's going to be 6x, it's going to be less than 0. So x is going to be less than 0. So for our function to be concave down, the interval is going to be from negative infinity to 0, as for the solution of this equation. Now, as you can notice from these two equations, our function is negative when x is less than 0, and it's going to be positive when x is greater than 0 here. So this means that at the point 0, our sign of our second derivative changes. So that means that x equals to 0 is a point of concavity. But that doesn't mean that for each point, a point of inflection, excuse me for my mistake, but that does not mean that for each point of inflection, there should be actually a second derivative. For example, in the case of, let me clear the whiteboard really quick, fx equals to x to the power of 5 over 3. So if you like our graph, let me sketch the graph real quick. It's similar to y equals x cubed, because both of them are odd functions. So basically, as you can see, from 0 to positive infinity, visually it's concave up. And from negative infinity to 0, as you can see visually, it's concave down. Similarly to y equals x cubed, our point of inflection is going to be 0, as you can see it visually. But let's try to find the second derivative of fx at 0. So first we need to find the first derivative. First derivative is going to be 3.5 x equals to 2. And our second derivative is going to be equal to what? It's going to be equal to 10 over 9 x to negative 1 over 3. So as you can notice from here, if you solve the equation where fx is going to be greater than 0 to find the concave up, you'll see that 10 over 9 x over 1 3 is going to be greater than 0. So x should be greater than 0. I skipped some calculations because I'm running out of time, so bear with me. Yeah. For f double x less than 0, our function is going to be, so let's just write this real quick. X should be less than 0. As you can notice, in this case, for x at x0, the sign of second derivative changes. And as I mentioned earlier, for when x is less than 0, our function is going to be concave down, and when the second derivative is greater than 0, our function is going to be concave up. Now, if you try to find x0, as you can see, the second derivative of fx does not exist when x is 0 because you cannot divide by 0. So from here, always when you're trying to find the point of inflection, always focus on where the sign of the second derivative of a given continuous fx changes. Now let's start some problem solving sessions. I'm just going to solve a single problem because I'm running out of time. And as great minds do, you will listen to classical music while solving the problem. So in the background, we will have a nice classical music. I hope you enjoy it. So basically the question is, we have a function for y is equal to x over 4 power divided by 4 minus 2x squared plus 4. And for visual interpretation, then you sketch the graph. But to be honest, you don't need to sketch it. I'm just sketching it because it was visible on the question. So our graph is going to be something like this. Now it says find the ranges where our y function is going to be concave up and concave down. So to do so, we need to first find the second derivative of y to find the concavity spot. So first derivative of y is going to be equal to, so it's going to be equal to x cubed minus 4x plus 0, and the second derivative of y is going to be equal to 3x squared minus 4 plus minus 4. So from here now we have to find where our second derivative of y is greater than 0 and where it is less than 0. Let me just check if everything is correct, and yes, everything is correct. Everything is correct. So y double dash is going to be greater than 0 when, so let's solve this equation real quick. 3x squared should be greater than 0. So 3x. So I'm going to factorize this. So basically, let's just factorize this. I will have square root of 3x minus 2 times square root of 3x plus 2 should be greater than 0. I don't mind the board because I don't have enough space. So, and if you try to solve this, so for x here, our zeros are going to be x equal to positive and negative 2 divided by square root of 3. So let me just write this here to find in which intervals our function is going to be positive. So for any value of x larger than 2 over 3, let's say a million, it's going to be positive. Any value between these 2 points, let's say for 0, it's going to be negative, because negative 2 times 2 is negative 4, and a million is just going to be positive. And for negative million, this is going to be negative, and this is going to be negative, so our value of the function is going to be negative. No, it's going to be positive, because 2 negatives create a positive, yes. So, as you can see from here, our function is going to be, our second derivative of function is going to be greater than 0, when x is in the range of negative infinity to negative 2 over square root of 3 united by, shout out to Manchester United, but Manchester City is always better. Yeah. Anyway, square root of 3 to positive infinity. And if we have to skip this point on the graph, I don't have the precise coordinates, but logically, at this point our graph is concave up. As you can see here, our arc is pointing toward upwards. So this point should be negative 2 over square root of 3. And same here, as you can see, our function is concave up as well here. So our function should be 2 over square root of 3. And in the between, our function is concave down. So that means that our so in the between, our second derivative of our function is negative, so it's going to be concave down. And if you would mind, which points are the point of inflection? As you can see that at point negative 2 over square root of 3 and at point 2 over square root of 3, our second derivative changes its sign. From in here it changes its sign from positive to negative, and in this point, at this point, it changes its sign from negative to positive. So these points are called the point of inflection. Anyways, this was all that I had to say. I have talked about concavity. I hope that you guys actually understood something of my explanation, because usually people say that I am extremely bad at explaining stuff, and I hope that you understood stuff. If you have any questions, feel free to just message me, and that's all what I have to say. Professor Gurbanov out.